There's a preferred way. Another way is just doing it in a more difficult way. But either way should do the job. I'll do it really quick. Show you the two different methods. The more standard way, which is method 1. So any term, because there's a single A here, so any term contains the A, you do an OR logic, so eventually they become A, right? So it's going to be A or C, D, E, B. Okay, eventually this becomes A, B, or B, C, D, E. But looking at this one, you can do a, so AB will be in parallel. And then you got 4. B, C, D, E. And here will be AB, B, C, D, E. Okay, so 2 in parallel first. This is the only way we can do it for a 2 parallel transistor, right? Because the output has to be on the side. In the middle, it gets stuck in there. So do this first, and then 4 in parallel. Remember, 4 in parallel would be this, this, and this. Okay, remember the patterns for 2 in parallel, 3 in parallel, 4 in parallel, 5 in parallel. Okay, so be bulletproof, right? No matter how I do it, you will be able to do it. Okay. Now this one is easy because we expect A and B's to be here, and here's a certain order here, so we want to follow that order, A, B. Right, the 4 in series, the order here doesn't matter, so I will just label, just follow this order here, which is B, C, D, E, B, C, D, E. Okay? And that's method 1. For method 2, you could factor B out. And it becomes B and A, C, D, E. Okay. And for the bottom here, it has to be B first. And then you got A here and C, D, E, right? Okay. Look at this, see if we can figure that out. So this is 5 transistors on the top. 1, 2, 3, 4, 5. How do we handle this? So first, if you look at this one, it's 2 in parallel, so it's B and A getting split over here first.
Dr. Lee,
oh, sorry.
Thank you.
So it has to be this first, right? B and A, 2 branches. And you don't want to connect it this way, right? Because the output and output here, they are not shorted together. So you're not supposed to do that. Nope, don't do that. So B is B, A is A, right? So B and A is this one, B is this guy, A is this guy. So it comes out, you got 3 in parallel, just do this. Right? And then you short these 2, right? And then you have the NMOSes. B first, because this is B, this is A, and these 3 doesn't matter. So when this comes out, I want this to be B. Is that possible?
Yeah, I think so.
How?
We put it on the left one.
So this is B, right?
Yeah.
So go through B first. That's easy. Just 2 branches, right? Just 2 branches. One's 1 transistor, another one has 3 transistors in series. So coming out here, how should we do that?
Well, it has to be A, wouldn't it? Oh, I guess it could be a parallel again.
How could we do this? This, right? It's A. So this doesn't matter. So it's a C, C, D, E here. So I'll label it C, D, E. Okay. So that's feedback to this quiz. Then let's look at the midterm. Yeah, I really don't have time to reorganize everything. I just directly copy and paste and making snapshots if I can. This is a solution from the lecture notes. We had a quiz on this, and I directly just wrote the answer during the lecture the next day, and so that's the solution here, but not very nice. But you know that for this one, if I'm asking you to, so this circuit, the circuit over here could be more resistors in the network, so you should still be able to simplify it. The 7 is equivalent, and then to find out the time delay, right? The time delay here is just simply our RC circuit. So convert whatever here into its VTH and RTH, and then it becomes a very simple RC circuit like this. Okay, and the V's and so the voltages over here doesn't matter what the voltage is. I may ask you what that value is, but if I don't ask you what the voltage here is, which is still fine, since you can always find out the time delay from input to output is going to be 0.7 RC. So you do need to find out the R here, but not necessarily the V, right? So 0.7 RC will give you the result. Time delay, okay? Superposition, and the superposition is very important theory in circuit theory, and this is a DAC, but it could be a different circuit form. But if you know how superposition works, you should be able to figure that out as well, right? So this one requires you to isolate one voltage source, or apply one voltage source first each time, right, and short all the other ones, and convert everything into its 7 is equivalent. We have done this several times. Just go back to the videos and notes, right, and then treat the following circuit as a load to calculate the voltage at the VL using superposition, right? But the circuit here could be slightly different, if you know Thevenin's and superposition, you should be able to find the answer, I think. Okay, so study this. If you know how to do this one, I believe you'll be able to do the other one, a different circuit. Okay. If I'm creating a different circuit, I don't know yet. I haven't made it yet. I'm just thinking it could be something different, right? Depending on if I do morning exercise, so I can get more creative and be energetic. Let's no.
Those are two are
Huh?
DAC, right? There's an analog converter, or like a start of it.
Oh yeah. Yeah, it's a DAC, right? Yeah, R2R DAC.
Does this review have all the concepts of the midterm, or will
Yeah.
go to microcontrollers where there's 10% that is not?
It covers pretty much everything. We'll see. Whenever we finish this one, I'm gonna tell you.
Okay.
Yeah. So C5 layers, there will be a picture from the layout from the lab. Okay, so we have done a lot of labs, right? So I'm gonna find out one of the lab pictures, the layouts from there, and then I'll probably just show you on the projector because I don't have a color printer, so I would just show you that picture and draw a line and let you draw that, because these are too simple, I think. We have done too many of these ones. So I'll just find out something from the lab's layout pictures and let you draw a line and let you draw the cross-sectional view from that. Is that okay? We did it once, right? We did that once, I think, during one of the quizzes. And some fundamentals like IV curves, that's required. You just have to know what that looks. VDS, VDS set, VSD set for the PMOS. Going up. So IV curve, yeah, I versus VDS, I versus VGS, VTH, VDS set, and saturation, all the different regions. And so the transistor device, cross-sectional view of that, because all the other ones are focused on mainly the other layers, but for the transistor itself, right? If there's a well tap, right? Could you still draw that cross-sectional view and explain what body effect is, right? Things like that. And inverters, stronger PMOS, stronger NMOS will shift your switching point to a certain direction. You should be able to figure that out as well. And here's a summary of all the different number of parallel transistors and their state diagram. So these patterns, you need to know that really well, I think. Okay, 3 in parallel, 4 in parallel, 5 in parallel, things like that. So star DC state diagram, we just did a quiz on it, right? We did multiple times of this one during the class, so watch the video and lecture notes. You should be able to figure that out. Number 9, the ISR latch state diagram, state table, the truth table, right? Different states. We just did a quiz on it a few days ago. And here's another one is application of the ISR latch, right? It's called the debunk circuit. You probably have heard about that from many different classes. So debunks is a switch when someone push it or switch it from one state to the other. There will be a mechanical vibration, will cause instability of the signals to the input because it's vibrating. Whenever you push it, it's not directly giving you a solid contact. It's vibrating, it's bouncing back and forth. So you are getting a vibration instead of a very clean signal, which is causing issues. So the application of using the ISR latch, one of the applications is to connect the circuit in a certain way. And when you switch this one from here to here, if there's a vibration here, so for example, right, like this NAND-gate ISR latch and a VDD here is a pull-up resistor. So usually what's the value of the pull-up resistor? common values of pull-ups? Let's say 10K, right? 1K is too small. 2K is, somebody use 2K, but the reason for that is I want to use a smaller number of resistor, but it's definitely bigger than 1K. Smaller value of the resistor will give you a more current, so you are able to drive the circuit under a higher speed. But if you don't really care about the speed is not a limitation, then just use 10K. It's always use 10K. Okay? It's a very safe pull-up resistor value. And so first, there's a problem with the circuit. I'm not telling you where, and I'm just explaining what's going on here. But there's an issue here. I'll probably ask you to fix it first. And so the idea is, here's the input, here's the output, right? So the output will be directly being fed into the circuit as a switch's output. And we're adding a debouncing circuit in the middle to debounce it. So if you want to give a 1 of the input from the switch, you should receive a 1. If you want to give a 0, you should receive a solid 0 or solid 1, right? Without bouncing back and forth, like, to get rid of this part. If you are switching to 0, if you don't debounce it, it's going to show this, right? If you debounce it, it's going to be a very clear 0 or a very clear 1, like this. You can imagine during your microcontroller loop, if you are trying to detect, if you don't put a debounce software in there, right, you are just detecting, hey, when this is 0, do something. However, it's just keep coming back and forth and give you so many different zeros, and you wouldn't be able to know when that got started, right? So in that case, especially for digital signal, right? Digital signals, the serial communications, they have 1 zeros happen really quickly. And for example, here you got a 0, and that's your actual signal, and you got 1s after, right? How could you tell like which one's the data, which one's the noise, the vibration, right? So that's why we need to debounce it. So for this one, the reason that this guy can debounce it is because it's using its memory state. Okay, so for NAND gates, what are the 2 inputs to give you a memory state? 1s or zeros. I mean, it's AND logic, right, or NAND logic. So zeros will kill it. So it has to be 1s, right? 1s is not changing anything because this is the output. The Q naught is feeding back, and Q is feeding back. If you got 2 1s, it's not changing these values. This Q is still being inverted. Got a Q naught is being inverted. Got a Q, and Q comes over here. Got a Q naught, and Q naught. Q naught is stable, right? So that's the memory. So it has to be 2 1s. All right, it has to be 2 1s. So whenever you have this one like slow motion, right? There's a high-speed camera recording a slow motion. The switch is doing this, right? So whenever this departs this node and traveling to this node, okay, at the moment, whenever this departs, there will be vibrations. And you can see this node was shorted to 0, right? So there was a 0 volts. And this is the pull up. So this pin was what? If you don't touch it before T0, what's happening here? What's the voltage here? 0, okay? 0, right? So whenever this one departs, this guy, this becomes what? So there's no grounding circuit anymore. What's the voltage here becomes? It's being put up. It's a 1, right? However, this switch is not ideal. Whenever you put you switch it to here, it bouncing back and forth. It's like touching and not touching for several microseconds. That's a mechanical feature of that metal. It's gonna do it. Okay, it's gonna do it. So there will be a 1 0 1 0 like this. Okay, and then it reaches this point, and there will be a bouncing as well before it makes a solid contact. So first, what's the problem of circuit? How do you want to fix it during this based on this kind of theory? You see, this one, it was 0 and 0, right? So what's the problem? We don't want a 0, 0. I just copied this from I searched it and found it from Google, and someone posted to a tutorial or something, but it's wrong. I'm just telling you. I told you there's something to fix, right? So what's the problem?
There used to be a 1.
Where?
Over the bottom.
Yeah. So we don't want 0 here. Okay? Okay. So let's assume that this is 1, right? So both are 1s. Both are put up. Now, none of them should be put down. Right? So both are put up. So if you short this one to ground, you are getting a 0 here. So it's a 0, 1 or 1, 0. You are getting always inverted inputs, which is it's supposed to be inverted, right? So it's either 0, 1 or 1, 0. Okay? So but now it's a 0, 1, right? 0, 1. And whenever this one departs this node, it's traveling, and this one is bouncing in between 1 and 0. So before this leaves, it's R and S, right? R and S. So it's actually a 1 here, right? Before time 0. So now this starts traveling to this point, and there will be a vibration. Does that matter? Is it going to affect this guy? No, it's either setting or memory. That makes sense? It's either setting or memory. So whenever this guy reaches it, the first time it reaches it, right, it's going to give a 0, right? And this one, after the vibration, this becomes what? This becomes 1, right? Because it's being put up. Okay? And once this guy touches it the first time, it should be a 0 first, right? Before the vibration. Okay? And then there will be a vibration after that. So before the vibration, it's going to reset it. And the vibration won't change anything because of the memory. Make sense? So that's a debouncing circuit. And it could be a NOR gate based debouncing circuit, and there will be different pull ups and pull downs and different signals, just let you know. You need to be able to fix it, right?
Yeah, so that bottom section is a VDD instead of ground, correct? That it'd be
For this one,
yeah.
I won't tell you.
No.
Yeah.
I think that would make more sense.
Yeah. No, that's a good question though. Yeah. That's a question for you guys during the exam. Okay, study this a little bit and draw a NOR gate version and figure that out as well. Okay. Number 11, determine the number of quantization levels of the DAC. This is a homework problem. Right, it's a homework problem. I didn't see any issues during the whole when I graded that problem. So if you have questions about it, you can send me an email. I will just tell you the answer. Okay, how to work with that. Because this is the range here. That's the range of the analog signal to resolve, right? That's the analog data, temperature data.
Yeah.
So you need totally 150 minus 50, this many levels, right? This many quantization levels. And it's a 5 volts. This many levels, within this accuracy over a range of this.
Well, you need a range of 200.
Huh?
Yeah.
This, right?
Yeah.
This total number of quantization levels. Uh-huh. You want to make it accurate, maybe +1. Right? So equaling 0 over there. So it's totally 101. 201.
Yeah.
Divided by this, right?
So it'd be like 2 would be
That's
20.
this many levels. And you need this many levels, and 0 to 5 volts is asking for the resolution of the ADC. You need to know how many bits do I need, because this is the power supply's voltage, right? This many levels,
I need 5 bits.
and versus 1 is 1 LSB. This total numbers, and I need a 5 volts, and this is correct. 2 to the x, right?
It should be 5 bits.
Hmm?
So you have
Do we need a 5 volts?
Because you have 21 levels you have to quantify, right?
Mm-hmm.
So you 5 times 21.
We probably don't even need the 5 volts over here,
Yeah.
right? So this is total number of levels that equals to this, right? And then we can find out x, right?
That's,
Mm-hmm.
yeah.
So that's all the levels need to be resolved, right? You don't even need the 1 here. Just all the levels will be the quantization levels for the ADC, and you can calculate for x. All right.
And then is the resolution the same as the levels, or is that the? Because you ask at the end.
No, the resolution is the number of bits. Always for ADC and DACs, whenever people ask you for the resolution, it's always number of bits.
Okay.
But rarely they're expecting the smallest voltage they can resolve. But usually, no, I don't think so. Usually, if they ask for the resolution, it's always how many bits. Okay. And since the reference voltage can change, right? So the ADCs usually takes different reference voltages. If you have different reference voltage, then the minimum LSB can change, will be different, right? The minimum voltage can be resolved, can be different. So usually it's just a number of bits. That's a professional way of answering that question, especially during interviews. So a digitally programmable signal, 14 bits, 10 volts, generate DC output voltage. What is the smallest incremental change of the output can occur? (14-bit) DAC, 10 volts. That's just 10 volts divided by 2 to the 14th, right? N-well resistors. So this is, I don't know if I gave you guys the solution to it, but it's something you need to know. There were some confusions about it from the homework assignments that I graded. Here. N-wells, let's see. Okay, this guy, right? This guy. So if we model this N-well resistor into this RC circuit, the equation to calculate the time delay from the beginning point to the end point will be 0.35 RC N squared. So N is number of squares you have. And it was derived in this note. So you don't want to directly use 0.7 RC because it's not. The reason for that is, remember that we calculate the time delay from A to output. You know, these are the N-well resistors, right? N-well resistors. And the PN junction has a junction capacitance. That's why we are getting capacitors over here as well, right? So we divided that whole capacitance into unit capacitors, and we divided the whole resistor into square resistors, like this, unit resistors. So, and we calculate these, this is R squared, C squared, right? So 0.7 RC plus 0.7 times 2 RC, because we're calculating 2 R's, right? So it's called the propagation delay, and every capacitor contributes 1 time delay. And for this capacitor, when we count the contribution of the time delay, this one contributes the whole thing. You have to look at the 2 resistors, because from this point to this point, it has 2 resistors. It's 2 RC, it's 2 RC. And for this guy, it's a 3 RC. So it becomes 0.7 RC plus 0.7 times 2 RC plus 0.7 times 3 RC, right? And then you factor out 0.7 RC, and eventually I'm getting 1 plus 2 plus 3 plus N, right? So N is how many squares do you have in there, okay? And so you can generalize this form into this form, and it becomes, so 1 plus 2 plus n equals 1 plus n times n divided by 2. That's the equation we used. And because we assume that n is a large number, at least larger than 10, at least. So we assume that n times n plus 1 is just n times n. So we simplify that this part to be n squared. We ignored n plus 1 because n is larger than a lot larger than 1. So we just ignore the 1 here. So it's n squared, and 2 is 0.7 divided by 2, so we're getting 0.35. So it becomes 0.35 RC n squared. So n is how many squares do we have? How many squares? So which is W over L, okay? W over L is n. That is for this problem. And then the next one, just more examples, just showing more examples, but just basically just cross-sectional views, cross-sections, drawings. And for TI's DFF circuits, this guy, we spent like 1-2 lectures, probably 1.5 lectures to cover this one. So definitely this will be put in, into the midterm exam. And I will probably run a simulation and show you the digital input and clock signal and let you draw the output. I'll include the set and reset. At the moment it's being set, at the moment it's being reset. So you need to show the signal at the Q accordingly based on the circuit. So I think the way to study this is just follow the lecture, and the lecture I recorded, right? And then go through the whole process that I proved that this guy was a D flip-flop, the rising edge flip-flop. So go through every single voltage node, so know the how each node behaves. And I think that will prepare you well for that problem, because you cannot remember, you cannot memorize everything. But if you understand how it works, it will become very easy when it comes to the timing diagram. Okay, and it will be closed book and closed notes. So you can bring a calculator, and if there's something that I think is necessary to be appended, I'm gonna append it to the exam. But it's gonna be closed book, closed notes. Okay. Same to this one as well. I'm gonna ask you, definitely it's a D flip-flop, it's pretty simple, but I'm gonna ask you how the voltage is gonna change at A, B, or C. Okay, not just the Q out, not just Q, but could be A or B mainly, because this is pretty simple. It's not being controlled, right? So C is just Q naught, but mainly these 2 points.
And with that, do you kind of want more values of what they would be given scenarios, or more of like a word description?
There will be simulation diagrams from Reality Spice, okay. And I will run the whole simulation, and I'm gonna probe these ones, and I'll use the painting tool to remove the plots of the voltages over here and let you draw it yourself.
Okay, so we'll draw the simulation.
Yeah. Okay. Same for this guy, right? I did one demo during the class, right? Shows you how I find out the waveform of this one. That video was recorded. You studied that video to prepare for a similar problem like this. Okay? It's recorded. And one thing here, design a inverter So design an inverter that switches at 2.5 volts, switch at the middle. So this is from the lecture notes, okay? So this one shows you that how to derive this equation, and this could be provided. and I'm gonna give you different values for the mobility, just some fake values, because the values provided by the model file is already known. You know it. So eventually, remember, we got a conclusion here, right? So from the, I think from the textbook's model file, we know that the NMOS from this one, the PMOS needs to be 3 times wider than the NMOS in order to switch it in the middle. Because the PMOS they have lower mobility. The holes have lower mobility compared to the electrons. So that's why PMOSes are less mobile, you can say, or less sensitive. So you need a 3 times wider of the PMOS to make it as strong as the NMOS, with only a third of the width compared to the PMOS. So they have the same strength, and you are able to switch it at the middle, 2.5 volts, right? I'm gonna give you different values of the mobility instead of just 3 to 1. It's gonna be something else, and let you design the inverter to make a switch at 2.5 volts. It's not very difficult. So I'll probably provide you with this equation and let you reach to this point, or maybe directly give you this guy. But either way, it will be doable, right? From here to here is also very easy. Just do just simple algebra. Okay. All right. Last one. Last one will be a practical digital block. It's just a application, but nothing is new actually. I'll give you a truth table and digital block. So this example shows you a decoder, 2 to 4 decoder. So 2 signals being decoded into 4, and it's basically just a little 1 is being shifted to the right. That's the 4 Qs, the decoder. Okay, and the 2 inputs is from 0 to 0 to 1 1, and there are 4 outputs. I mean, is this the only output could happen for a decoder? No. Remember in if you did the embedded system with me in the spring, so you can have ones here, right? You can have ones here. It doesn't matter, right? You have ones at all the different places. So in that case, you just derive your. This will be the problem in midterm. Okay, I'm just letting you know. So if I give you a truth table and shows you the ones at different places, and do you know how to find out the min terms? For the output, like it's gonna be Q0 equals what, right? The min terms. Like for example, this one, right? I'm gonna show you this column. So that digital system has 4 outputs. For this guy, you're having A naught, B naught, right? A naught, B naught, or A, B naught, this guy, or AB. Okay? And now you got a logic expression and how to convert this one into a logic and layout, right? So it's gonna be a practical digital block and from concept to a layout circuit. If for example you can reach to this point, what's next? And probably not 3 ones. I will just get rid of this guy.
It'd be simplified, right?
Yeah, you can simplify it, definitely. You can simplify it. But let's say just, for example, this guy. Yeah. I mean, for UI logic.
Well, they turn that to transistors, right?
Yeah, this is actually pretty simple. This is too simple. Let's edit this back. It's not fair, Curly. We'll see. I don't know what the results will be, but so this one, A naught or A, B naught, and this is what? 1. Okay?
Yeah.
This is actually, I think we have a conclusion of this form, right? So this is probably, I can't remember. I mean, just assume that this is not being simplified any further. A B or B not, right? Or do you start from here from to get a AI logic?
I mean,
2 bars, right?
yes.
Okay.
Yeah.
Then that's your job. Okay, 2 bars, and then use De Morgan's law. Okay.
I don't really understand how you got the midterms in the
Yeah.
first place.
Yeah. So this is something you have to study, right? So it's from the logic class 2 years ago you took, right? So you have a truth table, you have 4 outputs, you need to deal with each output each time, right? Because each output has one certain digital circuit. Since each output gives you one logic expression, and you are converting that logic expression into a digital circuit, so everyone needs a certain digital circuit. Okay, so for example, we start looking at it, start from Q0, right? Q0, you are picking up the ones. You're looking at the ones. Okay, we have 1 here, 1 here, 1 here, right? So 3 ones. Ignore the zeros. That's a conclusion. That's a method. Okay, look at the ones, and then look at the ones. See what are the inputs giving you that 1 here. These are the 3 inputs, right? 3 inputs. So for the inputs, if you have 0, 0, that midterm is called A not B not. So if you have a 0, you put a bar on the top. So this is A not B not. For this guy is 1, 0, so it's a A B not. Okay, for this one is A B because there's no 0, right? That's it. Yeah, that's a rule. That's a procedure we have to follow. Okay.
And would we have to do it for each Q?
Yeah, just 4 circuits, right? Just 4 circuits.
Okay.
Mm-hmm. Or like, thank you, Dr. Lee. I'll make sure that you guys can finish it within that 55 minutes. Okay. At least for most of you guys. At least half of the class should be able to get it done within 55 minutes. Okay, I'll try to control it within that kind of difficult level. What's that?
Do you want us to do the schematic with like PMOS, NMOS transistors, or like the gates?
Oh, definitely not the gates. The gates will be 2 years ago logic stuff, right? Here is going to be AOI logic. We want to simplify the circuit, minimize the footprint. Okay? I'm not testing your logic stuff, it's just basics. It will be used for more advanced level circuits, right? Instead of just directly logic. 7 more minutes. I don't want to cover new things today. Any other questions?
I'm good.
Okay? And this is posted to the announcement. Okay? This is the announcement. Feel free to. What's that?
How many problems?
I don't know yet. I think, for example, if this guy can test your logic, AOI, and layout, I'll probably just have 1 problem over here, cover all the stick diagram and everything, and then expect 1 problem like this, and expect. I don't know yet. I don't want to tell you some false information, so I haven't made it yet.
So much that can go on there.
I haven't made it yet. I mean, did you learn anything since the beginning of the semester? This is the things we have learned, right?
Yeah.
Not too much, but something.
Well, it feels like most of this is application different in a lot of other classes. Like taking a logic and combining that with like analog circuits and stuff.
Yeah, it's just whatever I told you. So answer your question, nothing else.
Okay.
So these are everything here. But we'll change the numbers, change the format, but whatever will be put on the test is already told you guys. Okay. All right. That's it.
Well, thank you.
Okay. Have a nice break.
Yeah, I'm gonna.
Yeah. And labs due Tuesday, not Monday.